Oh, cool. Awesome. Thank you. Is it on? Okay. Cool. Okay. Okay. So I think it's 9:30, so let's get started. Today I'm super excited because I can talk about uncertainty estimation in deep learning today. And it's a really interesting topic, and I hope that you guys are just as interested in this as I am, because it's a very important thing. And I hope to kind of get that piece across. And I'm going to be also introducing a few different ways how we estimate uncertainty in deep learning, right? So there are several pieces that I'll be going into today. I'm going to be starting to kind of talk about the problem setup. So why do we actually need uncertainty estimation in deep learning? What does it actually mean to estimate uncertainty in deep learning? And how does it relate to what we as humans understand as uncertainty, right? After that, I'll be talking about two different main pieces of uncertainty, namely aleatoric and epistemic. Those are like two very big buckets. And we're very interested in both of these different types of uncertainties. After that, I'm going to be presenting two different parts of this, right? So the first one is iterative uncertainty estimation, and the second one is single pass uncertainty estimation. Both of them are super important and really encompass of where uncertainty estimation is right now. And after that, I'm going to be going into applications. So that being said, let's kind of dig into a very well, popular example, right? So who's team blue here? Blue? Really, guys? Really? Blue? Okay, then the rest is team gold, I'm guessing. Rest of us is team gold. Okay, I'm also very much team gold. Okay, so very interesting. So you already see that just by the way this kind of divided already the lecture today, right? So you can already see that we are not really certain in our decision whether this thing is blue or gold, right? That kind of gives you a notion of what we understand as uncertainty. Now let me get a bit more concrete, right? And let me actually give you a more difficult one. So which one is pneumonia and which one's healthy? Okay, so who's for pneumonia left? Okay, who's for pneumonia right? Interesting. Okay, left. No. So left is healthy, actually. So you were wrong. So what I'm trying to get at over here, even though even though I'm using two very different examples, is that for us humans, we typically associate uncertainty with decisions, right? So in the case of the blue and the gold, or blue or gold dress, it was the decision of whether it's blue or if it's gold, right? In this case, we were talking about the decision whether it's pneumonia or healthy. And just intuitively speaking, if this would have been a real world scenario, you wouldn't have typically told me, well, the left is definitely pneumonia or the left is definitely healthy. You probably would have told me, let's get a doctor, because I have no clue, right? And that's kind of what we really want to have these systems in view, right? We really want a system to be able to say, if it's not really certain about its prediction, and in an ideal case, also give you the response, let's get a doctor, right? That's what we really want these things to mimic. And if we want to move this over to, well, deep models, as I already mentioned, right? We reflected or associate uncertainty with decisions. If we translate to the model, that translates to predictions. So if you think about this particular example that I have over here, which is autonomous driving, if the left is the input image, right, you have like some kind of prediction in the center. In this case, I'm showing you a semantic segmentation map, right? And on the far right, you would want to see where it's very sure about its prediction, where you have a very low amount of uncertainty, and an area where you have a high amount of uncertainty. So think about over here, in this case, the bus is highlighted, right? Because it's just looking at the picture you see here on the left, the bus is only half in the picture, right? It kind of blends in with the background. So you can see there's a bit of higher difficulty here, which also correlates with the uncertainty in this case. So what I'm trying to get at over here is that we're trying to look at what uncertainty means in terms of predictions of a neural network, right? And now, why is this important? This is actually a really important topic just based on safety. And I mean, I bet you guys can already think about a bunch of different scenarios, but I'm actually showing you one very particular one, which is one of the first car crashes due to assisted driving systems, due to this Tesla, right? So what happened is that this Tesla drove into this truck because it mistook this truck for the sky, right? So basically classified this humongous truck you see in the center and just said it was the sky. And well, you can already imagine if you would have a map, right, or if you would have like some kind of mapping that looks like something here on the right that would make this truck in the middle massively red, right, would light up, you could already imagine that you could potentially make a lot better decisions, or you could essentially encode into the algorithm that it should take a lot of care going forward. So that's what we're really trying to do in this lecture. We're actually going to be talking about how we can incorporate this into deep learning models. So where does uncertainty come from, right? That's kind of the next part that I want us to understand before we dive into actually discussing how we can estimate it. I'll be talking about three different things, namely the noise during data acquisition. The second one is variations in model configurations. And the third one is unknown data. So let's kind of dive in to give you guys a sense of what all of these three sources of uncertainty actually are. So first one, data noise, right? Very straightforward, means that in the data acquisition process, when we actually collect data, there are different noise sources, right, that can essentially play into us having a stronger uncertainty into our prediction. So if you look at, once again, this traffic sign recognition model, right, and I'm giving you a stop sign, right, I could have a very clear day where the stop sign is super visual, or it could be raining, right? Or there could be snow, or different other distortions that you see, which could occlude the stop sign. Now, the second example that we're showing over here, which may not be directly obvious, but is also super important, is actually human label uncertainty. So think about the pneumonia and healthy image just now. I would even argue that some doctors, right, even if you have a lot of experience or less experience, could classify these differently or could disagree on different, well, diagnoses, right? And that's essentially what you can have in variations among different labels. In this example here, right, we're showing you a picture of I think this is a frog actually in CIFAR 10, right? So could you really say what this is, right? Exactly. So that's what I mean. You could have a different, there could be different labels that are associated with it. And if you train a network with that, that could lead to severe problems. Now, second one, right, is the variation among model configurations. So we've already learned how neural networks are trained, right? And that we initialize the weights at the beginning. And just by initializing weights differently and using a different stochastic optimization process, you can already imagine that these networks can converge to different areas, which can essentially result in two different models, even though you train it on the exact same data, right? So that alone already gives you a sense of how many constraints the data allows you to give you and how much uncertainty the data allows. Now, the third one is unknown data, right? So if you have a lack of knowledge about it in a certain domain. So think about it if you only have two pictures of frog and you want to classify or know what a frog is. You can already see that there's very little that you can extract from these different things, right? Now, in this case, I'm actually showing you a third class. So imagine you have you're training on these two different classes you see down here, and now you're testing and you have a third class and that's over here, right? So there's no knowledge you have about that third class. So you can already imagine that you would want the model to reflect uncertainty about this class, about this outlier class. So that kind of brings me to these different pieces over here. And I'm putting these in two different buckets because that's kind of the different types of uncertainty I'm going to be talking about in a moment. Namely, there's data related uncertainty, right? So the stuff that comes from the data. Remember the stop sign that I just showed you with the rain happening, the acquisition process, stuff like that, right? And then we have insufficient model knowledge, right? So where the model does not have enough knowledge about the data and can't extract as much model information about the data to essentially give us the correct or that essentially results in uncertainty within the model. So before I kind of go now into the technical terminologies here, I want to take a short break and kind of see where we're at. Are there any questions about the general notion of where these different sources of uncertainty come from? If we're understanding what we're trying to do when I talk about predictive uncertainty, right? The uncertainty in prediction. Is this clear? Is the concept clear? Cool. Then I want to talk about two very important terminologies, namely aleatoric and epistemic uncertainty. Aleatoric uncertainty, and these terminologies you'll actually hear a lot also in no matter where you go to and you'll be working with deep learning, these are probably things you've either already heard or you will hear if you're talking about uncertainty. Aleatoric is exactly what I just described in terms of data uncertainty. So things that are related to data noise, things that are related to the acquisition process, to label noise, to disagreement among experts, right? That's this part of it. And epistemic is related to the model. So the way you typically define epistemic uncertainty is it can be explained away if you would have unlimited amount of data, right? So think about that scenario where we only had two examples of a class, or think about instances where you didn't know all of the classes. If you would have an infinite amount of data, you could explain that uncertainty away. And that's what this epistemic uncertainty is about. Now, these two terminologies, I just put them into this particular grouping because they are so insanely important. But now let's kind of dig in and talk about different ways we can estimate uncertainty in deep learning. And I'll be talking about these two areas, namely the iterative uncertainty estimation methods and single pass uncertainty estimation methods. So we group these into these two different categories simply because iterative uncertainty estimation methods are estimate uncertainty by essentially passing the same image through a bunch of different models or through a single model, meaning we iteratively estimate uncertainty by evaluating predictions a bunch of times. Now, single pass uncertainty is kind of the extension of this by just passing it through the neural network in a single shot and estimating uncertainty. Those are the two main blocks I want to discuss today. And let's kind of start with the iterative uncertainty estimation piece. So the idea is pretty straightforward. You iteratively generate a bunch of different predictions, right? And then you can already imagine that the amount of disagreement among these different predictions, depending on how you generate them, should ideally reflect the uncertainty that the model has within this particular data sample, right? So the idea is to take an image over here, you iteratively generate several model outputs, which where this is kind of where the methods differ. Then you take all of the predictions, you combine them in some different way, and that gives you an uncertainty score. So that's a very high level kind of map of how this works. I'm going to be showing you now two concrete examples of this, namely deep ensembles, and the second one is Monte Carlo dropout. Both of these methods are probably one of the most commonly used ones that I've seen in uncertainty estimation and deep learning. So let's kind of jump into, well, this iterative uncertainty estimation framework. Or actually, let me take a quick pause beforehand. Is this piece clear? Is this kind of, is this clear what we're trying to accomplish here? That we're iteratively going through them? Okay, cool. Great. So then let's kind of talk about ensembles. Oops, here we go. Oops, why isn't this? Okay, whatever. Okay, so the idea of ensembles is actually very simple. So if you think about this iterative uncertainty estimation framework and that you're trying to essentially map uncertainty because the predictions are very different, ensembles work by essentially generating all of these different predictions by training a bunch of different neural networks. So the idea is you train not only just one neural network, but you train like 3 or 10 or however many you want to train, right? And you can imagine that when each of these, due to these different initializations, they all converge to different areas in the weight space, right? So you have a bunch of different neural networks, and depending on what they predict, that already gives you a sense of what they're uncertain about, right? So if they disagree with each other, or if they're very much in agreement of each other, gives you a sense of where the neural network is uncertain. If the data has a lot of constraints, all of these models would ideally converge to the same spot, right? And they would all have the same prediction. Whereas if it's very uncertain, right, they would kind of converge to a bunch of different spots, which would result in, well, a very different prediction, right? Or would give you a very uncertain piece of it, right? And that's really what we're trying to do over here. And the final prediction, right, is the average of these. So you can imagine that, and this is a very common way of doing things in deep learning. If you ensemble things and you average over a bunch of different predictions, you tend, or you can actually achieve a plus in performance, which of course makes, or in a lot of, I wouldn't say always results in a plus in performance. It can result in a plus in performance, which is what the final prediction of this model is. Now, the second piece, of course, is the uncertainty scores, which is the spread and the mean. So you're going to be seeing these two things pop up a bit more throughout the lecture. And the reason is because these mean two different things. I'll go more into detail on these. The spread is actually the epistemic uncertainty, and the mean is going to be the total uncertainty that we're going to be, I'll be showing that in a moment. So let's kind of get this a bit more concrete. There are different ways you can do this. One standard way of generating ensembles is by essentially training a bunch of different models. Now, the way you can train a bunch of different models can change, right? So you can either train all of the different models on the same data. You can essentially divide all of the data into different blocks and train ensembles on different blocks, right? Or you can essentially train a different architecture, right, for all of these different ensembles, which also gives you a bit of a spread and a mean and an average. So there are a bunch of different ways to do it. In this case, we're listing just one of these, which is dividing the data into a different partition. Once again, this same principle here applies, where the model essentially converges to different areas, right? So is this piece clear? Are we clear on how ensembles work? No questions? Okay. This is, by the way, one of the best, or typically a lot of papers compare against this method, simply because it has one of the best uncertainty estimation scores out there, or it's one, yes. That depends on the way you're doing it. That is a way to do it. What it results in, the idea of it is to make the models differ more among each other, depending on how the data is set up, right? but that you can do both. So I've seen both in practice. And like I already mentioned, you could also have different architectures here as well. And that, of course, also depends on for instance, if you take a ResNet architecture, the loss function is typically a lot more smoother than like a VGG one. So you can imagine you would also get a difference in convergence properties here as well. So there are a lot of different ways you can essentially generate these ensembles. Are there any other questions to this? Cool. Okay. So the next one I actually want to talk about, and ensembles also to some extent represents this particular or are a derivation or can be put into this framework, is called Bayesian inference, right? And the idea is that you estimate a weight posterior. So given a data set, right, you essentially want to estimate which weights or which probability of weights are possible. Meaning you don't look at a simple network anymore from a deterministic perspective, but you actually look at it in terms of where the weights can converge to and the probability distribution of a weight. So what this means is a simple weight parameter within the neural network is not a simple point anymore, but a distribution. And well, actually, I'll try and color this in here. So what we previously looked at, if you have like two different weight parameters, W1 and W2, right? What we previously looked at is that they always converge to one single point. If you train a neural network, it would converge to a single point, right? Now, if I were to train several neural networks, I would get several points on this particular one, in this particular two-dimensional block, right? Does that make sense? Now, that gives me, in turn, a distribution, right? And yes, that represents a weight constellation. So if you think about like a simple perceptron, right, it would be W times X. And in this case, we only have W1 and W2 times X, right? So I'm just showing you a two-dimensional one, but like obviously it would be more complicated. The notion that I'm trying to give you guys over here is that we're looking at weights not anymore from a single deterministic point, but that it's actually a distribution that you're looking at this case. Now, why is this important? Because you can essentially start estimating a network, or at least you can describe a network not anymore from a deterministic view, but with this particular distribution. Now, the distribution, on the other hand, is characterized by the data set, right? So if you think about your, that's exactly what I'm showing up here with W given X. You could actually also see a WX given Y, right? Both of these, which is the total data set that you have, right? So given a data set, which are the different constellations your network can converge to? So now if you use naive Bayes, right? If you just use Bayes, that will give you this particular equation you see up here, which the posterior of the weight given your data set, right, is equal to, well, this posterior times your weight prior, right? And now what this integral, this fancy looking integral essentially is essentially the probability of your, what you can imagine that essentially being is the probability of your label given your input sample X. So essentially what you see at the bottom, it represents the Zusammenschluss, darn it. Sorry, I sometimes miss the vocabulary. It essentially represents the behavior between input and output, so the labels and the data. That's essentially what this probability distribution is. And that thing is super, super intractable because that's exactly what we're trying to estimate. You're training a model for data, given data, estimate the label, right? But to essentially have the probability distribution, of your label given some kind of input data X, right? If you would have that in the first place, you wouldn't need to train a neural network because you would already know the relationship. That's the word I was looking for. The relationship between your data and the label. So in other words, this thing is super, super intractable, and you essentially want to approximate this posterior, but there's no way in just simply doing it with naive Bayes. That's actually what I'm trying to say here. And if you would have this, you would essentially be able to sample it a bunch of times, which would give you a lot of different logics, which is what I'm going to be showing you in a moment. So now that we say we're going to approximate this posterior, right, which is this piece over here, we're going to find some way to approximate this posterior. The idea is actually very simple. If you have this weight distribution that I just mentioned, right? So if you know this distribution over here, you do not need to have particular instances of the neural network, right? You could just sample from this distribution. And if I sample a bunch of samples from this distribution, that would give me a bunch of different predictions that I could in turn then combine again, which would give me, first of all, a very good prediction of the model, while at the same time also giving me a measure of uncertainty, depending on how much these predictions differ, right? Now, there are a bunch of different ways how you can approximate this, as you can already imagine. So if I show you this posterior again, in the previous slide, there are a bunch of different ways you can approximate this particular distribution. There are different optimization methods where you, instead of essentially just converging to a single point, you're actually converging to the distribution. And after a while, each optimization step represents a sample from that distribution. But there's actually a way simpler way of doing it, which is probably one of the most or a very common way of using it in industry and in academia, which is called Monte Carlo dropout. And the idea is very simple. You use dropout during training. So everyone knows what dropout is, right? Everyone is familiar with dropout? Cool, nice. So the idea is you use dropout during training, meaning we randomly drop out different weights. And then at the same time, we also apply dropout during test time. So even though this may seem unintuitive way of using dropout, right? You're just starting to zero out weights. If I actually draw this up for you, right? And I apply dropout 3 times during testing, right? And I have a neural network, right? Whatever, right? You get the point. And I start just randomly taking out these 2 weights, right? The next one, I randomly take out this weight and this weight, right? And then in the next one, I just randomly take out this weight, and this weight, right? So by zeroing out different weights, all of these give me a different prediction, right? And just intuitively, you could already think that by doing this, it would give me some kind of sense of how sure the network is about its prediction, right? Because if all of these predictions are the same, the probability of my network being very certain about the prediction is going to be very high. Whereas like if it weren't, it'd be lower. Hence, this idea of sampling dropout at test time directly relates to this. And it directly relates to us trying to, if we look at the math under it, even though I'm not showing you the exact derivation of all of these things, it really amounts to trying to approximating this posterior weight distribution that I just said. So different samples, by zeroing out weights at test time, I'm essentially giving you instances of this weight distribution, right, that I just showed you, that really gives us a sense of how many constraints the data had and how much information the network has about this particular data point. So let's kind of put this a little bit into math, right? So I already just gave you an example of using dropout a bunch of different times during test time and then essentially combining the predictions in some way, right? So the idea is if we take the final prediction of the model, which is the probability of our label being some kind of class C, right? Given some kind of input sample X. Now, first we need to sample a bunch of different weight distributions, I just said, right? Different weight constellations, which is by applying dropout during test time, I take the same input and pass it through the same network a bunch of different times, right? Typically, these numbers are actually very high, so it can be even up to 50. So I'm passing the image like 50 times. Actually, I've seen even more than 50. So 50 is just a common number that I've seen, right? So you pass it through this network, let's say 50 times. And then each of these 50 output generations, you pass through a softmax, squash it through a softmax function, which essentially gives you a probability distribution for each of these, right? And then by averaging all of them, I'm essentially I'm combining all of these by a simple average. That would then be the prediction of my model. Now, if I put this into our previous framework, so remember I just told you that we're trying to estimate this posterior distribution W given the data set, right? So what this translates to is that this dropout distribution, right? So this probability, this Bernoulli distribution of dropout turning things on or turning things off is exactly this weight distribution. And we're actually sampling from this Bernoulli distribution at test time. Does that make sense? Yes. So softmax gives us a probability number, right? It gives us a number between 0 and 1. If we recall what softmax actually is, if you remember what the softmax function essentially is, it's the exponential of the output of your neural network given like the sum over all different exponentials. Oops. So if you think about an output vector and this dimension here being C, okay, so the different components of that output vector, the softmax function essentially is the exponential of the output of that particular point in your neural network, right? Divided by the sum over all of these. And that gives you a number between 0 and 1, which you can conveniently interpret as a probability score.
Why do you want that here?
Because the outputs of our neural network, we want our output of our neural network to be a probability distribution.
I guess my question is, why not just average all of the logic, the raw logic score, and then softmax that time?
So both of them essentially work, right? You can do both, but essentially the idea is that you want a probability distribution in the end. So yeah, that's kind of I want to take an extra slide to really highlight what the difference between both of these dropout things are, because it's very essential that you know that this is not the standard version how you use dropout. Dropout is actually used for regularization purposes during training, right? So that you essentially force the network to use a bunch of different weight parameters for its prediction, and not just include these and not just include a few handpicked ones, right? So standard dropout, you use it during training, and you essentially don't use it during testing. And during training, you essentially apply a probability score to each of these weights and just turn them on or off during training, right? The idea is very simple. By turning off the weights, you force the neural network to use or rely on the prediction of all of these different network parameters or that aren't turned off, and that can happen stochastically. Now, in contrast, the thing that I just presented to you, right? We apply it both during training and inference. So we use dropout during training, and it still regularizes the neural network. But most importantly, during test time, right, we still leave dropout on and randomly switch off weights during the test time. but we feed the same image through the neural network a bunch of different times with a bunch of different sampled inference or with a bunch of different sampled dropouts, right? And with a bunch of different shutdown weights, and then we average the result. So there's a very important difference that you have to see over here. In one case, we're doing this averaging at the end, right? Which also refers to marginalization, by the way, if you've ever heard something about Bayesian inference. Whereas in the other end, we're not doing that, right? We're just passing through the image once versus a bunch of times. And now let's kind of go into, or actually, let me take a break over here. Is Monte Carlo dropout clear? I know the principle is very straightforward. The math behind it is not as straightforward, but is the principle clear? Are we clear what we're doing? Okay, cool. Nice. Okay, so I just presented these two different major versions of iterative uncertainty estimation. And these represent a big part or are frequently used in practice, actually, because they are very reliable. This one is very, very simple to implement, right? You just turn on dropout during test time and you train it with dropout. So you can already imagine super easy to implement. You don't need a fancy model or anything. This one here, also very, very simple, right? I just train a neural network, the same neural network even, I can just switch out the seeds. So like the ideas behind them are super simple to implement. Now, what they all have in common is that they all kind of result in these multiple predictions, and that we have a mean and a spread as an uncertainty score. So I want to take some time to make us kind of understand how this mean and the spread really relates to uncertainty. And why I want to do that is so that when you guys run off into industry or wherever you guys go, and there is a machine learning model and you want to estimate uncertainty, and you're like, oh yeah, I heard this, right? This is super easy. I just use Monte Carlo dropout, or I just train 20 different neural networks. But it's more than that. I want you guys to be able to look at the output and understand what you're seeing and how it relates to how certain or uncertain this neural network is. And that's where I think this picture here is actually very powerful, right? And before we jump into this really daunting looking equation at the bottom, I already mentioned that we estimate uncertainty in both of these methods, right? We create a bunch of different predictions, and then we have an average and we have a spread of these predictions. And I want to talk about how these relate to this uncertainty. Now, if you have a bunch of different models, right, and it doesn't matter how you get them, either you get them through Monte Carlo dropout, or we get them through training a bunch of different neural networks, if they all result in the same prediction, right, you're probably going to be certain that it's confident. And that's what you can see over here. So imagine you have a 3-class problem, right? So the 3-class problem in the softmax setting, where you have one class up here, one class up here, and one class up here, if all of the different predictions and all the different probability scores kind of all go into the same area, you can already see that we're very confident in this particular prediction, and that all of these different neural networks agree on, well, the essential output prediction. Now, the second one that we have is when they don't agree. And there are two different settings that you could actually think about them not agreeing. Namely, do they all not agree and all cluster around in the center over here, like this thing, right? So all of these network predictions will be different, but they're all still clustered around the center, versus if they're all just all over the place. And that's kind of the very important difference that you're seeing here between aleatoric and epistemic uncertainty, the stuff that I mentioned very much at the beginning. So do we remember what both of these terms are? Who remembers them? What's aleatoric? Yes, correct. Okay, that means epistemic uncertainty is correct. Right. Okay, cool. We remember that. Okay, win. So what I'm showing you at the center, and that's kind of what I want you to see, is that all of the neural networks here agree on being uncertain, that you can see over here. Because they're all clustered in the center, right? They're all kind of like going and saying, like, okay, we have a high agreement that we're not really sure about this prediction. And that's what you can think about, like data noise, for instance, right? If they all have a very high agreement of the data not having the right labels, they'll all be kind of like doing this. That would be the ideal case, right? Now, the second part is may not be directly obvious, right? But if the neural networks converge to a bunch of different spots, right, that essentially means we don't really have a lot of knowledge about the data. It's not giving us a lot of, or the data is not giving us a lot of constraints on the model. And we have a lot of areas that we can essentially converge to, which is the high epistemic uncertainty that you see over here. And that's really captured in this spread that I was talking about, right? So that's where you can see the difference between, well, spread and, well, the mean, right? Now, these things essentially at the bottom that I'm showing you over here capture the mean and the spread. What I'm showing you here is a measure of mutual information, which is epistemic uncertainty, which captures spread, right? Versus if you just look at this thing over here. So what you see over here, of this piece over here captures basically the mean of the uncertainty of each of these individual points. I'll go into detail in a moment of the different components of these equations. But what this captures is aleatoric uncertainty. It's actually capturing the mean of the different entropy values that we're getting from our output softmax, which at the end gives us aleatoric uncertainty. And the total uncertainty is basically the entropy in this prediction. I'll go into detail in this in a moment. But before I go into and dive into this equation at the bottom over here, is the sense clear of mean and spread and how they relate to uncertainty in these iterative uncertainty methods? So if I were to give you a picture and say, give me the uncertainty of the neural network of this picture, you would know that what I want to make sure here is that you would know that the spread essentially would relate you to the epistemic uncertainty if you're using Monte Carlo dropout versus the mean relating to the total uncertainty. Cool stuff. Nice. Now let's dive into this daunting looking equation at the bottom. So let me start with the right piece. And you already see just by looking at these two equations are actually very similar because they really are. The only difference is where this H value is located. So I'm using H and what I'm referring to here is the entropy. So if you remember last week's lecture, I presented entropy in active learning, if you remember, right? It measures the information content of a distribution. So given some random distribution that you have, and you essentially want to know how much information content that distribution has, you'll measure the entropy of that distribution. And if you think about, like, for instance, a single point being in the middle, right? So where each probability score for each class will be the same, then the entropy is going to be the highest, if you think about it, right? That would give you 1 over n for the probability score. And that's essentially the value that we're going to be using for entropy. Now, the aleatoric uncertainty is defined by taking the probability softmax, so the output probability of each individual model. You take the entropy of that, right? And then you take the average of it. That gives me the aleatoric uncertainty. That's this part. Now, the total uncertainty, right? I first average in the middle over here, and then I take the entropy of it, right? So, and the difference between both of these captures a measure of spread, right? It captures a measure of spread. It's the mutual information between either combining both of these and first calculating the entropy. And that's what's really you're seeing over here. So it's not as daunting as it looks, or at least I hope so. And that gives you the epistemic uncertainty in the end, which is captures the spread. Now, this is super effective. As I already said, it's like one of the most widely used uncertainty estimation techniques out there. And I want to show you an example here. Given some kind of image that you see on the left, you have a ground truth prediction over here. This is the prediction of the neural network. This is the aleatoric uncertainty that I'm showing. And this is the epistemic uncertainty that I'm showing. And what's super cool over here is you can see, well, where the aleatoric uncertainty, for instance, is like concentrated. You can see that it's typically around the borders, right? So where we have a lot of label uncertainty, where it's not really clear where we really feed into all of the, or where the borders of these different semantic segmentation maps are, right? Or you can essentially see on the epistemic end, right? You can see areas that will look very difficult to discern. Like for instance, over here, you see a license plate. It's barely visible, right? So it's like, it gives you a sense of which areas exhibit a high data uncertainty versus a high model related uncertainty. So you could imagine if I have a bunch of different pictures that would give me areas of clouded license plates, or that would give me would give me license plates that are not shaded. You could imagine that that would reduce this. Are there any questions to this before I move into before I move on? Cool. So what I just presented to you were two different methods to estimate uncertainty. And they were all around the point of generating a bunch of multiple models. Now, you heard me emphasize multiple models all the time because it means that it's, well, first of all, it's very accurate, as I already showed you. The images that I just showed you, I hope they had some effect and gave you a notion of how this uncertainty estimation works. But on the downside, it's super computationally expensive. Think about if you take Monte Carlo dropout. Instead of feeding the picture through it once, right? I need to feed it through it like 50 times, for instance, if I want 50 dropout samples. If I'm taking the ensembles, right? I need to train 20 different neural networks or 50 different neural networks, right? So if you think about how difficult that is to scale, right? And how difficult that is to, for instance, put it in edge devices. Think about a self-driving car. You can't put like 100, or depending on how big of a computer you want in your car, but you don't want to be driving around with a massive server all the time. Yes. Oh, no, so you just train 50 different neural networks, for instance, right? But you can like you can train as many as you want. But the idea is you train a lot of neural networks and they give you a spread and a mean and predictions, and they all mean something different. But yeah, it's a good question. Very central. Good that you asked it. So yeah, the point I'm trying to make is it's super costly. And it's one of the major issues of why these things are so limited in their deployment, right? I can't use them in edge devices. I may be able to use these on a massive server where computational cost is not an issue, or where, you know what, time is not an issue. If you think about a self-driving car again, I can feed the image in the neural network like 50 times and increase the latency by 50, right? I can't always do that. I don't have the luxury to do that. So that's kind of where this second notion or the second area of uncertainty estimation comes in, which is single pass uncertainty estimation. Okay, and last chance for any questions for iterative uncertainty estimation before I move on to this. Nothing? Okay, cool. Everyone's clear on it? Dope. Okay, let's talk about single pass uncertainty estimation. And I want to bring it back this example that I showed you last week, right? About active learning. And you notice that we were using something very similar, right? I brought in these difficulty-based approaches. Remember, so if you think about active learning and we were thinking about selecting samples, we were going for the ones that were the most difficult. You could also think of it in a way of being the most uncertain, right? Those are the samples that my network is the most uncertain about and that I want to select for label. And we were able to do that in a single pass, right? I could pass an image through a neural network. That gave me a value. Why can we just not use that directly? That would completely relieve us from this issue of having to lug around a bunch of different models or having to pass the same image through the neural network a bunch of times, right? So that's really what I want to relate this to. And that's brings me to this next slide that you see over here. And it's not that simple. And the reason why this is not that simple is that neural networks are infamous for being uncalibrated. And I'm pretty sure you guys heard about these examples or a bunch of these, but that's that these probability scores that you see at the output are not really indicative for how uncertain the neural network is. And what I want to show you here is an example of this. I'm giving you an inlier image over here, which is our toad, right? And the fish. You notice that we're a big fan of fish and toads. So we're taking the toad, which gives us a prediction of 0.98 and 0.02. And for it being, imagine this being a toad and this being frog. So we're trying to classify toads from frogs. Should have said that before. Now, if we give it a fish, which has nothing to do with a frog or a toad, what can happen in neural networks is they give you a confident prediction of 0.97 that it's a frog, right? So even though it should ideally give you 0.5 and 0.5, which is what you would want to go for, this is not really what happens in neural networks, and it's not really it's a very difficult thing that essentially gives us a lot of trouble in their predictions. We say, and this is also like something that you'll also hear a lot, is that neural networks are badly calibrated or uncalibrated, right? That's also very much used. So that's very interesting, right? That means it's yes. Yeah, but how do you know what the outlier image is beforehand, right? So it's not just like it's not just doing these kind of things. It's like it's trying to generalize to areas which we haven't even seen before and we don't really even know about beforehand. So you see that this problem is a lot harder than just simply just going for direct probability scores or deriving entropy scores from the output distribution of my neural network directly, right? It's not necessarily as simple, but there are still different ways you can essentially do this. And I want to essentially show you how several or different methods that exist that essentially capture uncertainty in a single forward pass. So do exactly what I just described and essentially result in attempting and solving this uncalibration problem. So let me kind of use some time to formalize what we're trying to do here. If you have some kind of input, right? So some kind of two-class problem, which is your input distribution over here. The idea is you push it through a neural network. That neural network is able to distinguish both of these classes very well. So it's able to essentially generate a representation space, if you remember that what I showed you last lecture, right? And that's able to give us these two different representations of these classes. And we have an outlier sample over here. We want this neural network to be able to map this outlier sample away from these two classes so that we can measure uncertainty with the distance to these in-distribution classes. So given some kind of input distribution and giving us two different representations, we want to be able to measure uncertainty, which is the score U, with the distance to the input distribution classes. Is this concept clear? Because if we don't understand that we're trying to do this, we'll have problems in a moment. Yes? That's exactly what we're trying to do. If it is, then you have an uncertainty-aware model. If it isn't, it isn't, right? Are there any other questions? Yes. Correct. It's the output of your model, exactly. Okay. Okay, so I just gave you this notion that we're trying to measure uncertainty with distance. And if you want to formalize this, that kind of gives you this very daunting looking definition that you see up here, right? So the idea is that we're trying to find some kind of statistic, right, that is able to measure the distance of a point to an in-distribution point, or to these points that we are well aware of during training that are very certain, right? So before we go into this big piece up here, let's just focus on this equation in the center. The uncertainty of some kind of sample X, right, should ideally be a statistic of the distance of your sample X to your training sample in distribution. That's really what this whole thing really is. Nothing more, right? So now the question is, how do you define distance, right? How do you go through this, right? And that's where the model comes in. But that's really what we're trying to do. We're trying to define a statistic that measures the distance. Now, the distance, on the other hand, right, is you essentially can describe it as the distance of your sample X to, well, the expectational value, because this here, your input distribution here, this distance here is your input distribution, right? So if you get the expectational distance between these, that's what you essentially want to model, if I want to put this in math terms. And this whole piece up there is a fancy version of saying exactly that, right? It's the correct mathematical definition. So if I were to like wake you guys, or if you were to describe someone on the street, how we're estimating uncertainty, I would expect you guys to be answering this, which of course is a very high probability of that happening, but you know, like that's the general idea behind this. Now, there are two different pieces that we essentially need in order to estimate distance in neural networks. Actually, let me take a pause over here. Is this clear? Is this notion of distance awareness clear, that we're trying to estimate the distance? Very, very important. Okay, yes. Yeah, that was the example that I actually just showed over here, right? The idea is that you measure the distance towards your in-distribution sample. So it's not only about measuring the distance that it's far away over here, but it's essentially measuring the distance to the in-distribution sample here and the in-distribution samples here, right? That's really what the uncertainty estimation is about. That's why if it's in the center of the classes, you're still covered, because the idea is that you're still measuring the distance to its manifold, right? To the actual class manifold. Okay. So in order to estimate this distance, we need two things, right? The first thing we need to do is we need to be able to measure the distance. So let's say we have a perfect neural network that's able to like separate both of these, right? We need some kind of way to measure this distance. Now, there are a lot of different ways how to do it. The more interesting piece of it, and you can already see that I'm gravitating towards this, is we actually want the neural network to be able to give us a representation where it can separate these. That was very much related to the question that you just asked, right? How do we do this? That's really centered around this one, right? So given two different distances in the input domain, right, we want to be able to preserve that distance in the output domain. So if you remember, I was talking about feature collapse last time that essentially mapped them to the same point. That's an example of that not happening, right? That's a big problem with neural networks, right? So we want to give neural networks a chance to essentially do this. And that's really what these next couple of slides is going to be about. This second piece over here in actually measuring the uncertainty, this is typically also done with non-deep learning algorithms. So you typically put like a Gaussian process on it. I don't know if you've heard of Gaussian processes before, but there are like a lot of different deep learning or non-deep learning algorithms to measure the distance in these, which also intuitively makes sense, I can imagine, right? So it's measuring the distance is typically not the problem. There are a bunch of different ways to do it. The problem is the right side. And that's what I'm going to be, left side, sorry. And that's what I'm really going to be focusing on this lecture. So trying to preserve this information. And it's all centered, or a way to do this is enforce a mathematical property called by-Lipschitz. And what by-Lipschitz functions essentially are, given some kind of like input distance, right, x over here, you essentially force the model distance, right, so the model output distance for these 2 points to essentially follow these different upper and lower bounds. So given the norm over here multiplied by some kind of constant, and given the norm over here multiplied by some kind of constant, you want to sandwich essentially the distance of your model in between both of these. So let me kind of spend some time of how these relate to each other. What you see here on the left side, right, essentially means sensitivity. What sensitivity means is if this output over here, if we have a distance over here, we don't want it to be mapped to the same point. We want it to be sensitive to different inputs, right? So that's really what this left piece is. So given the distance of 2 points in the input domain, we want our output of our neural network to be bigger than that. Right? That makes us automatically sensitive, right? If we're bigger than the distance, if the distance in this domain is bigger than the distance in this domain, it's going to be able to be differentiable. So that's very difficult to do sometimes because, well, we're severely compressing the data in a lot of neural network applications. So if you think about this toad image, right? So it's 1024 by 1024 by 3. If we push it through our neural network, it's just 2 by 1 vector, right? So you can already imagine keeping this distance alive during this entire piece is not necessarily as straightforward as it directly looks. Now, the second part of this by-Lipschitz constraint is smoothness. And the idea is that you don't want a small distance in the input to essentially result in a huge difference in the output. Think about mean square error, for instance, right? Why do we not just use mean square error to measure uncertainty? Well, one key reason is because it's not smooth, right? Because the moment we like slightly change the image location, right, it directly blows up the mean square error. That's what you can see over here. And so if there's a small distance over here in the input, and we result in a massive distance in the output, that's what we essentially call as not smooth. So if you think about this example of a toad and a frog, so this is a false toad. I mentioned that last lecture, if you remember, right? And this is actually a frog. You don't want these to, you don't want to essentially blow this out of proportion. That's the idea behind it. So there we go. What I'm trying to say here is that DNNs, as they are, they're not always sensitive and they're not always smooth, right? That's a natural occasion of neural networks, which essentially also results in also not having calibrated results. And these two examples that I just emphasized on both of these really show you, or I hope give you a sense of where smoothness and sensitivity is and where they're not given in neural networks. Does that make sense? Okay. So if they're 1, right? If the bound is very tight, then it's equal, right? The answer is that would give you a very tight Lipschitz bound, which would in turn give you a very good reflection about the input distribution. So from an uncertainty estimation standpoint, it's great. Typically, it results in a worse performance though, because you can already think about the compression piece. So the mapping this big picture to a 2-dimensional vector. You want the neural network to be able to compress. You want it to extract information. And if you have a very tight Lipschitz bound, it's hard to extract more information. That makes sense. Okay. That brings me to well, this notion of single pass uncertainty estimation methods. So I just described what distance awareness is, right? I described to you what distance preservation means in neural networks. And I also described to you what distance awareness means in the output. So the moment we have that separated, those two different separated manifolds, that we can essentially measure uncertainty with the statistic. That was the distance awareness that I was discussing. So there are two different pieces that we need, right? The distance preservation one that I just mentioned, and the distance estimation in the output layer. And that's really what all of these methods do. They train a neural network, right? They apply some kind of constraint during training that typically results in distance preservation, right? And the output layer of this neural network is typically associated with a non-deep learning algorithm that essentially measures the distance with respect to the input, the in-distribution data, which really gives us the uncertainty estimation over here. So there are several methods that really do this. One of them is called DUQ, the other one is called SNGP. And I would say these are the two most famous ones. And then you also have DUE and this one over here, DEUP. They're all based on the same principle, meaning distance preservation and distance estimation in the output layer. So I want to talk about one particular one, namely SNGP. And what I want to talk about is give you a sense of how they estimate or how they enforce distance preservation in SNGP. The distance awareness piece, you can read the paper and take a look at it. That one's very straightforward. I'm going to be focusing on the distance preservation piece of this lecture. Namely, the idea is to enforce by Lipschitz. And the way you enforce by Lipschitz is by doing something you call spectral normalization. Now, what spectral normalization does is it normalizes the eigenvalues of the individual weight matrices to be between to be less than 1. And what it essentially results in, I'm not really going to be proving to you of like how the spectral normalization essentially results in the Lipschitz piece, but what it results in is this particular by Lipschitz bound. So you have some kind of alpha over here. That's the value you spectrally normalize this weight matrix in all of these different layers to. So you can essentially imagine that you do something like this, right? You essentially normalize it less than alpha. And by having this, this restriction over here, you can essentially prove that using a residual net architecture, so all of these methods use a residual network architecture, you can enforce both smoothness and sensitivity at the same time, right? And the two Lipschitz constants are given by 1 plus alpha and 1 minus alpha to the power of L, which is the number of layers. So you can already, the reason why I'm actually talking about this in so much detail is because looking at this and just intuitively speaking, you could already see that by having a very large network, a very deep neural network, these Lipschitz bounds completely go out of each other, right? So they go very far apart, meaning I can't really do a very good guarantee about either sensitivity or smoothness if this number here is very low and if this number here is very high, right? And that's kind of one of the big drawbacks of, like, for instance, SNGP, because it can essentially estimate uncertainty only if you have a very shallow neural network, right? So these are, I'm trying to give you a sense of where these methods are essentially also limited. So there are two issues here that I just highlighted. The first one is that in order to do spectral normalization and in order for it to work, you need to use a ResNet architecture. That limits your methods, right? It severely limits it. The second thing is it's dependent on the number of layers, which completely diverges your spectral normalization. Okay, so I know that was a lot of math, but what I was trying to really get you guys at is to give you a sense of how these methods work and essentially where the drawbacks of these methods are and where there are still things to look for, right? You already saw the spectral normalization only works if you have a residual net architecture, if it's dependent on the number of layers, right? And even if you can get it right, that leaves the distance awareness piece. But they're still very effective, and you do not need to pass the image through a ton of times, and you don't need a lot of neural networks to estimate uncertainty. So I want to take a quick break here. Are there any questions about single pass uncertainty? Okay. That leads me to the final piece, which is applications. And basically, anywhere where we use a neural network, especially safety critical applications, is where we're super interested in estimating uncertainty. So the example that I gave you earlier on, right? If you think about autonomous vehicles, you want to know how sure your neural network is about its prediction. If you think about medical data, would you ever want a neural network to classify or make a diagnosis about you even, right? If it doesn't reflect how certain it is about its decision, right? So even in active learning, right? I already showed you last time uncertain or difficulty-based methods, right? Same principle applies. How good is this uncertainty estimation? How effective are we in getting all of these things? So you see that it's super relevant for data selection, for safety critical applications. No matter where you go, these uncertainty estimation methods play a major role. And it's also what industry is currently is super interested in, because it's the make or break deal, or can be the make or break deal for your deployment of your technology. And that being said, I hope I gave you guys a sense of where uncertainty estimation is at currently. I hope I gave you a sense of how, or you feel like you're equipped to build a neural network that can estimate uncertainty. That being said, we're at 10:42, 10:43. So are there any questions? Cool. Glenn, thanks for coming.